Yeah, good morning all. So in our today's topic, so we are going to discuss about a topic called finite automata, finite automata to regular grammar. Finite automata to regular grammar. In the sense, you have been given an input called finite automata, and from that finite automata, what you have to find out, you need to find out the what is the corresponding regular grammar for that. Okay, now how do we do that? So in order to do that, so there are three different types of cases are there which needs to be considered over here. So let us go ahead and consider the case one. So we have case one, what the case one says. So the case one says that whenever we have an automata like this, so we have some state and this is also some state like this. Let us assume that we have two states and the name of this state is capital A and the name of this state is capital B. And in between these two states, there is a transition between these two states with the help of some input symbol. Let us assume that small a. Okay. Now, what is happening here in the case A? We have two states, capital A and capital B. So, and we have a transition from A to B. Now, whenever we have this type of transition between two different states, now the equivalent grammar will be written as follows. So, what is the state from which the transition has been started? The state from which the transition has been started is a capital A. So that is the reason this state is going to become like a variable. And what is the terminal? What is the terminal? Because of that, so we have a transition from capital A to capital B. So by reading small a, now we have a transition to which state? Capital B. Okay. Now this is how we have been converting the given finite automata into the corresponding regular grammar. Okay, so this is our case one. Okay, now let us go ahead and consider our case two. Consider the case two. So what is the case two is? Now the case two says, now I'm going to take the same, so copy the same diagram. So this the case 2 is like this. So now here what is happening is, so both A and B are non-final states. Now let us assume that we have a scenario where B is a final state. Where B is a final state. When we have B as a final state, then the transitions are going to be like this. So first we need to write a grammar. Please observe, whenever we have considered like some state is like a final state, then first we need to write the grammar predictions by considering that that state is not a final state. Okay, now what I am doing here, I am considering B is not a final state. By considering B is not a final state, I have written a prediction called a small a capital B. And then in the second scenario, what we'll do is we are going to consider that this B is a final state. This B is a final state. As B is a final state, now we are going to specify only the terminal symbol. You can see here, please try to understand. So the second scenario is very important scenario. What it says that, so whenever you have a transition to the final state, whenever you have a transition to the final state, in such cases you need to consider two things. So what are the two things you have to consider? The first thing is, so you need to specify or you need to write the grammar without considering the state like a final state. Now if you don't consider the state like a final state, now we are going to get the grammar prediction like this, small a capital B. And then if we now we need to consider the given state like a final state. So once we consider the given state like a final state, then we are not going to get this variable, and simply now we will be getting the so terminal or input only. So just because of which, So we have a transition from one state to the other state. Okay, so this is our case 2. Now let us consider case 3. What is case 3 is? So we have case 3. We have case 3. So what this case 3 is? Now let us observe that we have some state. We have some state like this. So where the same state itself is going to act like both initial state and the final state. For example, let us observe that we have some state where this state itself is going to act like both initial and as well as a final state. And let us give the name of this state like a capital A. Capital A. When we have some state which itself is going to act like both initial and as well as the final states in the sense, then in such cases, now we will be having the transition called epsilon transition. We will be having an epsilon transition. Okay, so please try to understand. So when you have some scenario like this where your initial state itself is going to act like a final state, in such cases now you will be having a transition something like A derives to epsilon. Okay, so now these are the three scenarios so which needs to be considered whenever we want to convert the given finite automata into the regular grammar. Okay, now let us take one small example. Now let us consider this example. For example, let us assume that this Q naught is our initial state. So this Q naught is our initial state and Q2 is the final state, and this Q naught, Q1, these are the normal states. Okay. Now this is the finite automata which has been given for us. Which has been given for us. Now this finite automata needs to be converted into the corresponding regular grammar. Now, what are the steps we have to follow? Now, if you look into this finite automata, obviously this finite automata will be having either all the three cases or any one of the case or any one or two cases. Understand? Now, using these three cases only, now we are going to define or we are going to write the regular grammar. Okay. Now, we are going to start our transitions from Q0, Q1 and Q2. So, what is our initial state here? Our initial state is Q0. Now, instead of using Q0, Q1 and Q2, now what I am doing, first I am going to rename Q0, Q0, Q1 and Q2 with with A, B and C. A, B and C. So that it becomes very easy for us to tackle with the regular grammar. Okay. Now I am going to specify the transitions for capital A. So what is capital A here? So which is nothing but Q naught. So in order to make you clear here, what I will do, I will write over here. So we are considering Q naught like capital A, and we are considering Q1 like capital B, and we are considering Q2 like capital C. Okay. Now what we have to do here, we need to write what are the Q naught transitions are, means A transitions are. Now if you observe from Q naught on 0 it goes to Q1, Q naught on 0 it goes to Q1, in the sense on A on 0 it goes to B, A on 0 it goes to B, and then search for any other transitions on Q naught itself. On Q naught we have 1, on Q naught we have 1 on Q naught and 1, it goes to same Q naught itself. Already we have renamed Q naught with capital A, so it will be 1A. And if you check other transitions for Q naught, we don't have any other transitions. Okay, so these are the transitions for Q naught. I mean A. Now we need to define the transitions for Q1 and grammar for Q1. But already we have renamed Q1 as B, so I am going to consider it like B. What is the B transitions here? Now if you look into this, so Q1 on 0, it goes to Q1 itself, in the sense, so 0 B, 0 B, and Q1 on 1, q1 on 1. Where it goes to q2. But here what is happening, so as we came to know that q2 is the final state. Q2 is the final state. Now consider the second case here. When you consider the second case, so you need to write one production by considering q2 as a non-final state, and the second production by considering q2 as a final state. Now, when you do that, why we will get a production like Q1 derives 1 Q2, 1 Q2, 1 Q2 in the sense we have 1 C or 1, 1 C or 1. Understand? So this is how we will be writing the productions for second one, which is B. Then go for third one. What is the third one we have? We have Q2 state, which is the final state. Now we have given a name called C. What are the C productions we have? C on 0 goes to B. You can see here C on 0 goes to B. So C on 0 it goes to B. Or so C on 1 goes to A. C on 1 goes to A. Now you can see here C on 1 goes to A. Okay, so this is how we are actually going to convert our given grammar our given finite automata into the corresponding regular grammar. Understand? Now let us take one more example. Let me take that example. Now let us take one more example. Now this is one more example where we have the initial state itself is going to act like a final state. Now this is my second example. This is our second example. Now what we have to do, we need to write the regular grammar for this finite automata. Okay, now just follow the same three cases. So what we have discussed just now. So as we have the states as A and B, no need to rename now. Now I am going to take the same as it is. So A derives. So first we try to specify the transitions. So what are the transitions we have? A on 0, please observe here we have A on 0. So A on 0 goes to where? It goes to the same state which is the final state. As this is the final state, now we need to consider two things. What are the two things? 0A or 0A or 0. 0A or 0. Then one more thing which we have is one more transition which we have is A on 1 it goes to B. A on 1 it goes to B. So here we need to specify A on 1 it will be B. So this is how we are going to write the A transitions. But if you look into the diagram thoroughly, so what we have here, I already told you that the initial state itself is going to act like a final state. As the initial state itself is going to act like a final state here, now we will be getting one more production. We will be getting one more production, which is the epsilon production. Which is the epsilon production. Okay, so please try to understand. So totally with the A, we will be having four different productions. So what are the four productions? One is with 0 and with by considering A as non-final state and by considering A as a final state, and one is with the input symbol 1, and the last one will be as the initial state itself is going to act like a final state. Now we will be having an epsilon transition. Then the next one will be B. Now we are going to write B productions. So what are the B productions? B on 0 goes to A. Please observe B on 0 goes to A. But we have identified that A is a final state. So it will be, the productions will be 0A or 0. 0A or 0. And B on 1, you can check it over here. B on 1, it will be 1B. B on 1 will be 1B. Now, if you look into this, the B is not a final state. B is not a final state. So, hence, we will be getting the production like this. Understand? Now, this is how we will be converting our given finite automata into the corresponding regular grammar. And here, very specifically, I told you in our previous classes itself, where I am discussing about the Chomsky hierarchy of the languages. So I told you that we have two types of regular languages, or we have two types of regular grammars. Regular grammars. So what are the two types of regular grammars? The first one is right linear grammar, and the second one is the left linear grammar. Okay, and what type of productions we will be having in our right linear grammar means, so always remember the variable should be appearing on the right hand side of the production. So if the variable appears, see here, if the variable appears on the right hand side of the production, we call it like a right linear grammar. And coming back to left linear grammar, then the variable has to appear on the left hand side of the production. Now if you look into this, so the productions what we have formed, what we have generated from the given finite automata, if you observe the productions, these productions, and as well as these productions, so very clearly you can understand that all our productions are what type of productions? They are all right linear productions. Right linear productions. So from this I want to tell you one thing, that so this is the procedure which we have followed to generate not the simply the regular grammar, but what I can tell you here is it will be right linear grammar. So the steps which we have discussed, the steps which we have discussed so far, the steps which we have discussed so far, these are the steps that we are going to follow, not to generate the regular grammar, but to generate what type of grammar? More specifically, we will be generating the right linear grammar. The reason for that is, if you look into the productions over here, on each and every production, the variable is appearing on the right hand side of the production. So hence we can say that, so we are going to generate the right linear grammar, so from the given finite automata. Okay, so that's it. This is how we will be converting our given finite automata into the corresponding regular grammar. Our next topic is, just now what we have seen how to convert our finite automata into the right linear grammar. In the same manner here, now you will be given a regular grammar. You will be given a regular grammar. From that regular grammar, we need to convert it to the finite automata. We need to convert it to the finite automata. The idea is very, very simple. The idea is very simple. So whatever we did over here just now for converting the finite automata to regular grammar, likewise here also we are going to follow the same steps. Okay, so let me straight away go with some example so that it becomes very easy for you to understand. So let me take, we have some grammar like this: a derives to small a capital B, or small b capital A, or small b. So this is A productions. Now the B productions are like this: B derives to small a capital C, or small b capital P. So these are the B productions. And coming back to C productions, so C derives small a capital A, or small b capital C, or small a. So this is how we have the productions associated with the given grammar. Now, if you observe thoroughly here, how this grammar is looking like. So this grammar is looking like a, very clearly you can say that this grammar will be not a simply a regular grammar. So more specifically, again I can tell you, more specifically, it will be the right linear grammar. So right linear grammar. Okay, so more specifically, it's a right linear grammar. Let me, right linear grammar. Now we are going to convert that right linear grammar to our finite automata. This is what we are actually doing now. Okay, now the idea is very simple. Whatever we did for the previous conversion, now we are going to follow the same. Now, here, whatever the symbols are there, variables are there, like a capital E, capital B, and capital C, all these variables are going to act like states now. So, capital A, capital B, and capital C. All these variables are going to act like states. Then the next one we are going to consider here is, so which one should be considered like a initial state. So what is the start symbol of our grammar? The start symbol of our grammar is capital A. Now that is the reason why we are going to consider that. So the start symbol of our grammar will be capital A. Now let me name all these states here. So this is capital A state, and this is capital B state, and this is capital C state. So far we have not decided what is the final state. Now, depending on the available grammar information, so we are doing the things. Okay. Now here the variables, whatever the variables available in our grammar, those variables are going to act like states in our finite automata. Okay. And then if you observe thoroughly here, we have a production called capital A derives small a capital B, small a capital B. Now from this we can say that once we are present on state A, by reading the input symbol small a, we will be having a transition to state B. Now that is what I am going to do here. So from capital A, there will be a transition to capital B by reading the input symbol called small a. Okay, then the next case comes on when we are present on state A, by reading the input symbol small b, we have a transition to the state A. In the sense, now this is our state A. Now we will be having the transition to the same state itself. When it is going to happen, it will be happen. So when we have the input symbol called small b. In the same manner, if you observe thoroughly, we have a transition called A derives to small b. A derives to small b. Now, when it is going to happen? When it is going to happen? So, this A derives to small b is going to happen if and only if your initial state, this state itself is going to act like a final state. When it becomes itself like a final state, now we are going to consider the third case. Okay. Now from this you can observe, when you try to convert this automata, whatever we have constructed, into the grammar, we will get productions like A derives to small a capital B, and then small b capital A, and then as A itself is a final state, now we will be getting the small b, this one. Okay, so this is how we have finished the conversion process of the first production into the corresponding automata. Now let us go for the second one, b productions. Just have a look at this. The b productions says that B derives to small a capital C. Small a capital C means from B to C there is a possibility of having a transition by reading an input symbol called small a. Now we will get a production called B derives to AC. In the same manner, B derives to small b capital B. B derives to small b capital B means now we will be having a transition from B to B itself, B to B itself, when we read the input symbol called B on state B. Now with this we can say that we have completed the automata construction part for this second production also. Now let us go ahead and see the last one, C productions. So we have a production called C derives to small a capital A. So this is our state C. So from C to capital A, there will be a production. So C derives to small a capital A. Now this transition is possible with the help of input symbol small a. Okay, and then what is the next transition we have? C derives to small b capital C. C derives to small b capital C. So from C to B, C derives to small b capital C. In the sense, from C to C, there will be a transition possible once we have an input symbol called small b. And then how we are getting this small a? We are getting this small a because this capital A is going to act like a final state. Now, if you consider the C productions over here, from C, we will be having a transition on B. So, C derives to BC. Okay. And then from C, we are going to have a transition on A to a final state. Now, there is a possibility that we will be getting two productions. One is without considering A as a final state, and one is by considering A as a final state. Okay, so this is how we are going to convert our given right linear grammar to the corresponding finite automata. Okay, now let us take one more example so that it becomes very clear for us regarding the conversion. Let me take one simple grammar over here. So here we will be taking one small example like A derives small a capital B, A derives small a capital B, and B derives small a capital B, or small b capital B, or small a or small b. So this is my grammar productions. Now, how many variables are there? As we have two variables, now we are going to take two states over here. Okay, two states. Now, out of these two states, now we need to decide which one is the initial state. So the answer is very simple. Whatever the start symbol of the grammar is there, that state or that symbol is going to act like a starting state or initial state. Okay, what is the start symbol of our grammar? Capital A. So that capital A is going to act like my initial state of my finite automata. Now we need to specify the transitions. As there is a production called A derives to small a capital B. Now from A to B, there is a production. There is a transition on input symbol small a and small a. Now coming back to B here, now there will be transitions possible. Please check from B. On reading input symbol A, there will be a transition to B itself. So here on B, by reading input symbol small a, you will be having transitions to the same state. Then if you observe thoroughly, on B, again by reading the input symbol, you will be having the transition to the same state itself. Now from this, after that, what we have? We have transition A comma B. Now from this, we can confirm that now the final state in our finite automata will be B only. Okay. Now if you consider the B productions over here, now it will be B derives to small a capital B and small b capital B. Now without considering B as a final state. By considering B as a final state, now we will be getting two production, small a, small b. By combining all those, we will be getting this production like B derives to small a capital B, small b capital B, A or B. Okay, so this is how we will be converting our given right linear grammar to the finite automata. Okay, now these are the four steps that we are going to follow for converting the given finite automata to the left linear grammar. So what are the four steps? The first step we have to do is we need to take the reverse of our finite automata. So I hope we already discussed how we are going to take the reverse of our finite automata during the closure properties also. Okay, the first and foremost step as part of reversal operation is we need to interchange the initial states to final states and final states to initial states. And then what we have to do, we need to do the transitions. We need to change the transitions. For example, if there is a transition from A to B, now during the reversal, now we will be getting a transition from state B to state A. Okay, and then what we have to do, once we did the reverse of our finite automata, then what we are doing, we are going to take the right linear grammar. Means we are going to write the right linear grammar. After doing the writing the right linear grammar, then finally what we will be getting, so we are going to get the left linear grammar. So after taking the right linear grammar, we need to take the reverse of it. So we need to take the reverse of it. Once we take the reverse of it, then we will be getting the final left linear grammar. Okay, now these are the steps that we are going to follow. Now let us see with some example here. Now let us observe, we are going to take the same. So let us observe, so we are going to take this example and we try to convert the same here into the left linear grammar. Okay, so this is our finite automata. This is our finite automata. Now this finite automata will be converted into the corresponding left linear grammar. So please observe, so first, as a first step, what we have to do, we need to find the reverse. We need to find the reverse of automata. Reverse of automata. So when we do the reverse of this automata, so what will happen? The initial state is going to act like final state and the final state is going to act like a initial state. So let me write all these things quickly. So these are the three states. These are the three states, and the three states will be like this: capital A, and this will be capital B, and this is, sorry, and this is capital C. These are the three states. Now, in our original finite automata, we have A as a final state. A as a final state. I mean, A as an initial state. Now, this initial state, now it is going to become the final state. Okay, in the sense, now here we need to if I want to make it very clear here, as the initial state itself is going to act like a final state here, now we need to introduce a new initial state with the epsilon transition. So let me introduce a new initial state here with some epsilon transition. For example, wait a second, so here I am taking a new initial state and I am calling it like capital S. So this is my new initial state. Okay, this is my new initial state. Now from this new initial state, now we need to specify the epsilon transitions. Okay, and this my A is my final state. A is my final state. So here let us go ahead, and this is yes, and from here we will be having some epsilon transitions, and this A is going to act like a final state. So A here is going to act like a final state, and then rest of the other transitions will be same. So from A to B, we will be having transition. We have a transition, and from here also we have a transition like this. So I'm writing the transition as it is, and B to B there is a transition on input symbol B, and B to C there is a transition on input symbol small a, on small a, and here we have a transition on small b, and here we have a transition like this. So we have transition on small e. Okay, so this is what the automata which we got. Then the next thing what we have to do is, now we need to do the complete reverse. Reverse in the sense, now what we have to do, we need to make this initial state to final state and the final state to initial state. After that, the next thing we have to do is, we need to do the reverse of all the transitions. Once we do the reverse of all the transitions, now we will be getting a new finite automata. From that new finite automata, we have to write the right linear grammar. So that right linear grammar, again we are going to write it in reverse. So with which we are going to get the corresponding left linear grammar. So now what I will do, I will stop over here and I will complete these steps. So rest of these steps in our next class. Okay. So that's it for today's class. So thank you very much for joining today's class.